thank you for the introduction and the invitation to speak this evening. It's really welcome. So, good evening all, and so this evening it's a bit of a blended presentation in that it's not only talking about bridges, it's also buildings, and the reason they go hand in hand you'll find out in a few slides' time. So if we move on to steel and steel concrete composite standards, I guess the first one that really sent us on this journey of harmonisation is the bridge standard AS 5100. And originally it was an Australian-only series of standards. There were 7 parts. And back in 2011, there was an initiative to actually revise that suite of standards. At the time, there was a Standards New Zealand put out a consultation to see whether it would be useful to develop these series of standards as joint standards. At the time, it was decided not to. The industry wasn't ready to do that. However, a subsequent consultation of the steel industry basically got the thumbs up, and the steel and composite part of this series was developed as a joint standard. So you'll see the actual denotation of this series is AS in brackets NZS 5100. Part 6 is the only joint standard out of that suite. So as well as the 7 parts that were in the original one, there was an extra 2 parts, and I guess one which was probably one of the most innovative ones was a design standard for timber bridges as well. So the 2 standards I'll be talking about today is the bridge standard, ASINZS 5100 Part 6, and the multi-storey building standard, ASINZS 2327. And whilst these are the 2 that I'll be focusing on, there has been quite a lot of other harmonisation activities. So as well as the design standards, there's been a lot of harmonisation in the product standards as well as the fabrication and erection standards. And basically this shows the structure of the steel standards in New Zealand now. So we have 2327, which is the joint standard for composite buildings, 5100 Part 6 for bridges, 4600 was there since 1996 for cold form steel construction. And one of my wishes, which I'd love to have got over the finishing line, was to try and join the existing domestic standard NZS 3404 with the existing domestic standard in Australia AS 4100. And as I'm going, MBIE have just agreed to actually fund that happening, but unfortunately I'm going to be out for that this time round. So underpinning those design standards is what I call the execution standard. So the reason why that's needed is that it gives all the workmanship requirements to ensure that the design assumptions remain valid within the design standards. And then the standards that then underpin the execution standard are the structural steel standards, which were published in 2016, which I was on, welding, fasteners, which has recently been published for bolts, 1252, and protective coatings, and again those have recently been published as well. So there's been quite a lot of work in standards over the last few years. So first of all, starting off at the material strengths that are permitted in the bridge as well as the building standard. So when we started in 2011 on the update of the bridge standard, one of the requirements was that compressive concrete strengths up to 100 megapascals needed to be included, and that was to align it with the Australian standard 5100 Part 5, as well as the Australian equivalent of NZS 3101. Also, NZS 3101 also recognises 100 megapascal concrete, so there was a requirement that that had to be included. In addition, the Australian steel structure standard also permitted structural steel of a yield strength up to 690 megapascals. So that also had to be included in these new standards. So at first sight, probably doesn't too bad, but that actually created a bit of a headache when we were looking at the composite provisions. Because if you considered other standards around the world, such as the Eurocode or the AISC specification, they go nowhere near those sorts of strengths. So what it meant was that rather than just adopting or adapting provisions that are in other international standards, we did have to really go back to first principles in a lot of cases, and this also required quite a bit of structural reliability work, which I'll talk to you about later on in the presentation. And because of that need to do the structural reliability work, we did go back to basics, so studs, beams, slabs, columns, all actually were re-evaluated from scratch, where we looked at the required capacity reduction factors to achieve the required safety margin. So that was quite a lot of work. So if we move first on to composite beams. So for those of you who've never done composite design, essentially if you have a non-composite beam where you have a concrete slab and a steel eye section, and there's no connection in between the two, I always describe it as basically two rulers. If you bend them, and the one slips relative to the other. And in those circumstances, if you had an I-beam and a solid concrete slab, you would get this, these strain and stress profiles if you're using plastic design. So basically, they bend around their two plastic neutral axes. However, if you connect the two, you develop a a perfect member which utilises the compressive capabilities of the concrete and the tensile capabilities of the structural steel. And that joint between those two elements is normally achieved through shear connectors. And that creates quite efficient structures. So sort of the headline numbers, why you'd want to consider composite beams is the bend resistance is increased by a factor of 1.5 to 2.5. Stiffness is increased dramatically, and by utilising those capabilities you can reduce the steel weight or potentially reduce the beam depth. It also facilitates lightweight construction, and because of the increased stiffness it's good for vibration as well as fire resistance properties. So because the shear connection is so important, I'll first of all take you through shear connectors. And I think something that some designers sometimes misunderstand is that all the design provisions for shear connectors in different design standards around the world, they all have been developed from these so-called small-scale push tests shown on the right-hand side of this slide. So irrespective if it was studs, channels, or some new shear connector, could be even powder actuated fasteners, they've all gone through these sorts of tests. And essentially the reason what's actually done in these tests, you might just about be able to see from the diagram, is that you have a short steel H section, there's a shear connector attached to each flange. Studs are shown here, but it could be any type of shear connector. A slab is cast on each side of the I-beam, and then once the concrete's hardened, load is applied to the tip of the I section, and the load slip behaviour is monitored for the shear connectors, and that's shown schematically on the right-hand side. So basically, the measure that's of importance here is the characteristic or design resistance of the stud. Obviously, we want to know how strong it is. But the thing that sometimes has been overlooked in the past is the slip capacity. The slip capacity is very important in that it defines the ductility of the shear connector. So in the past, there have been a wide range of interesting types of shear connectors. The helical connector shown on the top right-hand side, that was probably one of the first types of shear connectors that was developed in the 1930s in Switzerland. And then as things moved on, channel connectors, and bar and block connectors were also developed. But as the stud welding apparatus started to become more available, headed stud connectors really sort of took off, and they became one of the most popular forms of shear connector in composite construction. And one of the other distinctions that I'd like to make with these different shear connectors is that headed studs are normally defined as flexible connectors, and I'll describe what that means later on. Channel shear connectors are flexible in certain circumstances. However, helical and bar connectors tend to be what are known as rigid connectors. And if I go back to the slide, so flexible connectors tend to have this plateau, this ductility. Rigid connectors tend to have a much higher resistance, but have a much shorter plateau on the load slip curve. So having that flexibility is very useful when we look at design of composite members. So if we consider a simply supported beam subjected to a uniform distributed load, and we put certain load on it, essentially the beam deflects, and we would have a elastic longitudinal shear force shown on the bottom of this diagram. And if we were to examine the whereabouts the forces and slips were for the shear connectors A, B, C, D, those are shown on this on the right-hand side of this diagram. If we were to increase the load even further, essentially you start to get plastic behaviour forming at the ends of the beam in the shear connectors, and you can see here shear connector C and D starts to go on the plateau. And then if we increase the load even further, we can basically get all those shear connectors up on that on the plateau of that load slip curve. And it's very important that we actually have sufficient ductility that we're allowed to assume those all the shear connectors within the shear span of the beam can actually get up to their full capacity and go along this plateau shown on the right-hand side. If we didn't have that plateau, things wouldn't look so nice, in that essentially, as we get towards the end of the beam, you would start to get an unloading effect. And so this is why it's so important that, as well as resistance, the ductility is very important. So the magic number that's used in most design standards and is also included in ASINZS 2327 is that the characteristic slip capacity must be at least 6 millimetres. If it's below that, the shear connector would be considered non-ductile. So if you were to try and work out the slip of a shear connector in a composite beam, it's a fairly complicated process. Here we've done it before. It typically normally means using finite element analysis. And obviously we don't want to make things too hard as a code writer. So for the designer to allow for that ductility, we provide what's known as minimum degree of shear connection equations. So providing you satisfy some certain requirements, you can assume that the shear connectors won't go beyond their slip capacity of 6 millimetres. And this is shown graphically here. So degree of shear connection. So I'll explain this a little bit more. So if we have degrees of shear connection of 0, it means that there's no shear connection. If we have a degree of shear connection of 1, that means that you have enough connectors that would actually, which would mobilise the full compression resistance of the concrete or the full tensile resistance of the steel beam. Typically for economic designs, you tend to design for partial shear connection. So it's you would normally design a beam between 1 and 40% shear connection. And I guess the things to take from this graph here is that the amount of the degree of shear connection, thereby the amount of shear connectors you have to provide on the beam, increases as the span increases. It increases as the steel grade increases. and it also increases if you have a large asymmetry in the cross-section. And what I mean by asymmetry is the bottom flange of the steel eye section being a lot larger than the steel top flange. So anyway, this is a graphical representation, but in the standard 2327, there's a set of equations that allow you to work out these minimum degrees of shear connection. And most pieces of design software already have this all inbuilt within them. So that's the importance of ductility in shear connectors. The other obvious thing would be important is the resistance. And this is one of the examples where we did some, because the concrete strengths were so much higher than any other international standard, we had to go back to basics again and come up with some design equations for both 2327 and 5100 part 6. And essentially this was a reliability analysis which we at HERA were involved in, and if you're interested, this is the reference. You could get it from the HERA library if you're interested to see what went on. But I guess the headline figures you can see from here is that the green line is the resistance from the AISC specification up to the point where they have the cut-off in the compressive resistance of the concrete. The blue dotted one is Eurocode 4, and the red one is what's currently in 2327 and 5100 part 6. So you can see we really are mobilising the full capacity of the shear connectors from this reliability analysis. And why we were able to make that significant improvement was that in the reliability analysis we had much more test data available at our fingertips than either the AISC or the Eurocode 4 code writers had at the time when they were developing their rules. When we have a shear connector welded within profiled steel sheeting, typically the resistance reduces, and it's probably quite obvious, as you can see from the right-hand side diagram, that because you've basically got a void in front of the shear connector, there will be some sort of reduction. And to allow for this reduction, what most international standards do is they have a so-called reduction factor that the engineers multiplies to the resistance of a stud in a solid slab to enable you to give a capacity which will be appropriate for a stud welded in profiled steel sheeting. So I guess the main things you can see from here is that the important things are the number of studs within the rib, the width of the rib, which is given the denotation B0, the height of the profiled steel sheeting, and the height of the stud HSC. And it's very important that you have a sufficient projection of the stud above the sheeting height HB. So one of the things to watch here is that in some of the older standards there was no limitation on the number of studs that you could weld within a rib of a profiled steel sheet. In Eurocode, as well as 2327 now, it's limited to 2. You can put more in, but you won't get any more capacity out of them. And the other thing that's to note was that, and this is going back to some work that I'll talk to you about in the next couple of slides that I did in the UK, is that most of these modern trapezoidal decks tend to have this small reentrant stiffener on the tops of their crests, which you can see shown here. And $1 million question often is, well, what height of the sheeting do you use in these design equations? Do you use the overall height or do you use the net height? And in 2327, it's very clear that when you're using stud connectors, the net height is the one you should be using. And the reason why this has been, it seems a very, very small nuanced rule about the net height, but believe me, actually the base of it was involved quite a lot of testing in the UK. And basically the history of this was that back in the early 2000s, the first trapezoidal deck was introduced from the UK into Australia, and because it was a new type of decking used there, they decided to do some push tests, and similar to those which you can see in the top right-hand picture. And while we would be expecting a low slip curve like this shown in blue, so you get a slip capacity of 6 millimetres, what they're actually finding was something far worse, something like that. So it was almost half the ductility that we were expecting. And so first we, obviously from the UK's perspective, been using, trapezoidal decks for like maybe 20, 30 years. We just didn't believe the work. We did some of our own tests and unfortunately came up with the same sort of findings. And the million-dollar question that we had then was, okay, well, the push test is showing that you're getting a lower ductility. How does that really reflect in a full-scale beam? And this is, you probably recognise the picture from the invitation to this evening's presentation. This involved 3 full-scale beam tests. This was done at the University of Cambridge. And two of the things of note here is that the reason we did these tests was that one of the things that is absent in a push test is you don't normally have a normal force applied to the face of the concrete slabs. Whereas if we have a beam test on the left-hand side, you would obviously have the weight from the self-weight of the slab plus the uniform distributed load from the working conditions. So this was one difference in those 2 specimens. And one of the other things to note from these full-scale beam tests is that, unlike anything that's been done internationally before, you might just about see it in this picture on the right, is that we actually instrumented every single cross-section all the way down the beam to actually monitor the build-up of the force into the still section, and we also monitored the slip at every single shear connector position. So extremely expensive exercise, but we did that just to find what the behaviour really was in a full-scale beam. And champagne corks started popping. We found out that the performance in a beam was significantly better than that would be suggested in a push test. And where have we got it? It's badly shown here, but whereas in the previous slides where I showed maybe you would get maybe 3 or 4 millimetres worth of slip, we're getting 50, 20 millimetres worth in the beam test. So what that led to was us to come up with rather than having to do a beam test every time a new deck was developed, we decided to develop a completely new push test, which basically kept to the same principles but applied a normal face to normal force to the face of the test slabs. And the setup is shown on the left-hand side here. This was based. The tests used in this specimen was used in an amendment to the UK standard BS 5950. It's an option that's given in 2327, and it's also being implemented within Eurocode 4. So I guess the main thing to note here was the ductilities were strongly influenced by the normal force. Thing I should say, just so it doesn't have any confusion, the resistances were around about right if you didn't have the normal force. But it was, so the push tests were still valid for resistance, but they weren't really valid for ductility. So I mentioned the push test can be used on any type of shear connector, and another one that's just about to be introduced into New Zealand is powder actuated shear connector. And one of the things that this has been in use in Europe probably since the mid-1980s. Some of the attributes you might want to consider for this is that It can be shot fired through corrosion protection, so that's be great for maybe car park applications. It's good when you're renovating old buildings, making the existing steel sections composite. And it also, as you can see from the equipment, you don't have all these cables floating along the floor, so there are no sparks for health and safety requirements and no tripping hazards. And what this particular manufacturer known as Hilti, they did is instead of actually just providing resistances from push tests, they actually adapted the reduction factor formulae that are given in 2327 to make these equations suitable for their products. So I guess the thing to show here is that there didn't seem to be any reduction to the capacity when you put multiple powder actuated connectors within a rib of a profile steel sheet. And we investigated this at the University of Auckland here in Auckland. And we showed that up to 4 could still be used with no reduction in strength. The other thing which I should have shown here, but I was a bit short on slides, is the ductility is much better than headed studs, almost a factor of 2 better. So they tend to be very ductile indeed. So in 2327, one of the differences from the previous composite design rules in the New Zealand Standard 3404 is there's a number of different options on designing a composite beam, and it's shown graphically here on the left-hand side. So on the vertical axis of this, we've got moment capacity, and that's basically moment capacity divided by the plastic moment resistance of the composite section with full shear connection. And on the horizontal axis, it's degree of shear connection. So as you can see from here, if we get 100% shear connection, that's the maximum moment capacity you can get out of a composite beam. And essentially, if you have ductile shear connectors, they would be anywhere between E to min and 1.0. So within that region, if you're satisfying the minimum degree of shear connection rules, you can use plastic design principles. And there's 2 options. You can use what's known as the equilibrium method, which is that convex curve, ABC, or there's a more a conservative approach, which is known as the linear interaction method, where you can just linearly increase the moment resistance from the bare steel section up to 100% shear connection. So it's that line A to C. If, however, you've got non-ductile shear connectors, you've got an option here, either using line DEC or CF0. So in the previous version of 3404, if you didn't meet the minimum degree of shear connection, that was it. In 2327, there's a bit more options available to you if you still want to make the beam composite. The extra bit of information is shown here on item B, and this is a special case, and this is for when you use high strength steel. And one of the issues with high strength steel is that to fully plastify the steel section, you can actually get premature crushing of the concrete slab. So what this rule does is it gives you a reduction factor depending on the plastic neutral axis position in the steel section. So that's a special one. You probably won't use that frequently, but that's for high strength materials. And all of those design options we again looked at using reliability analysis. It's quite a complicated exercise. I won't go too much into depth, but basically you've got to look at the variation in geometry and the variation in the material strengths. Material strength shown here. This is grade 300 steel, That's the distribution of yield strengths you would get. And if you see on the top right-hand side, these are all the different variables that define the geometry that you would need to use in your design equation. So each one of those geometries could potentially vary by these amounts shown in this table here. So it's a fairly complicated exercise, but essentially what you have to do is look at the design model shown from that graph on the top right-hand side, compare it using all the measured properties, compare it against tests, see how well the model compares, and then it's almost like a what-if analysis by looking at if you were to change the geometry or change the strength, what effect would that have on the capacity. And one of those examples is shown on the bottom right-hand side. These are known as Monte Carlo simulations. So this is a simulation of a single beam test. So the real beam test was the red dot, but then if you were to repeat it over and over and over, this was 8,000 runs, you could see the potential scatter of results. And normally when we're doing design, we look at always the lowest probable capacity. So our design values would be down here somewhere. So as well as resistance for normal conditions, in 2327 there's rules for floor vibrations, and so those are essentially based on this design guide on the left-hand side. This design guide gives you what's known as a simple method, which is suitable for hand calculations, or a general method, which is more suitable for finite element analysis. The general method is the one that's actually given in 2327. And this method is actually fairly well recognised internationally now. It was used in this building in Sydney, and if any of you use the GSA OASIS software, it's also incorporated within there. So there shouldn't be any changes with 2327 adopting this. It just really, sort of it's a standard that you can hang your hat on now, that if you're doing a vibration design, you can say it's in accordance with 2327. The other thing that is included, which is really a jump ahead of many other international standards, is that the provisions for beams with web openings are also included in 2327. It took quite a bit of inspiration from this left-hand document. Again, we're ahead of the other international standards. Eurocode 3 and 4 are still considering implementing that within their documents. This has already been published. The only thing I would like to draw your attention to is that the rules in 2327 probably aren't that great in terms of fire resistance of cellular beams. So one thing to watch for these types of members is that they're a little bit different to solid web beams, not only in looks but also in their performance in fire conditions. And what tends to happen is the web post, which is basically the bit of steel that goes between these two circular openings, tends to heat up a lot quicker than solid webbed beams. So it's not covered in 2327, but the document I'd recommend people consult is this ASFP document. I think it's the Association for Still Fire Protection. It's a UK document. And basically there's two routes. If you use reactive coatings, such as intumescent coatings, I'm afraid tough luck, the manufacturer would have to do some fire tests. If you're using a passive protection, such as a cementitious spray, there's some design rules on what you do there, but it's not as simple as solid web beams. So, composite slabs. Why use them? Well, the sheeting tends to act as a working platform and a permanent formwork. Unpop construction can be achieved, which is great for speed of construction. It can also be used to stabilise the supporting beams if there's suitable fixing between the sheeting and the top flange of the ice section. And if the sheeting is suitably embossed, you can you can get shear connection between the concrete and steel deck, such that the deck provides some, if not all, of the tension reinforcement to the slab. So the types of decks that are accepted in 2327, we call it the clip hand profile on the left-hand side, re-entrant profile in the middle, and an open trough profile, which is the one that you're probably more familiar with. And although you probably just look at design tables of software, the basis for these rules, there's two options when it comes to the construction stage. One way to come up with the design properties is through using design equations, using ASINZS 4600. However, that's normally that's not normally used in practice. In most cases, deck manufacturers actually do tests on their new products to find the design properties. So one of the things that was missing before we wrote 2327 was that there wasn't a definition of what the standard test should be, and those are currently given in 2327. And there's also an appendix to tell the manufacturer how to evaluate the design properties from the tests. So you have to take into account that you know, there's the possibility that the strength of the decking could be weaker than that exhibited in the tests, and you have to take that into consideration. And just some examples of some tests here. So the top right picture is a full-scale continuous test. That's a 7 metre long profile steel sheet being tested to destruction at Imperial College in London. And this right-hand one, this is what's known as an end support test. So it's essentially a knife-edge support and looking at the crushing capacity of the sheeting when it's loaded highly in shear. The other thing that's in 2327, and which is a bit of a strange one, is there doesn't seem to be any rules either in the concrete standard, the steel standard, or even 1170 on what loads to use when you're designing formwork. So we've actually provided some rules there. These loadings are taken from the Eurocode, and essentially there's two scenarios that you need to consider. Essentially, you have this what's known as the working area. This is this area A, and that imposed load can actually move anywhere on the profiled steel decking. So when you're designing, you need to move that load A into the area that provides the most adverse effect. So obviously, when it's simply supported, you put it in mid-span. When it's continuous, normally it's the over the internal support tends to be the worst case. Only thing to watch if you're doing, now that we've got this joint standard, you may well be doing designs in Australia. One thing to watch is that Australia, they decided to adopt a slightly different construction load model. So please be aware that if you're doing doing some designs for that country, there will be a little bit of a difference. So that's the construction stage. And I mentioned earlier on that if you've got suitable embossments, you can get shear connection between the deck and the concrete. And the way that shear connection is evaluated is again from tests. So it's a bit like a push test. You can't predict it by calculations. You have to do some. You have to actually do some experiments. And the standard test is shown on this left-hand side. So it's essentially two line loads at quarter points. And the idea of the test is that the span of the slab is sufficiently short to provoke shear failure of the slab at the interface between the deck and the concrete. So an example is shown on the top right, and this is an example of one of the spent tests. Afterwards, you can see that the concrete basically has slid relative to the steel decking. And again, just to make you aware, although you probably don't look at this on a day-to-day basis, because it's all given to you in the design tables or design software, there's two methods of actually describing the longitudinal shear bond in composite slabs. There's what's known as the partial connection approach, which is shown on the left-hand side, and you can see from the diagram, it's very similar to what we have for composite beams. It's the same theory that, as the degree of shear connection goes up to 100%, you can't get any more capacity. Or the other option is a very empirical approach, which is traditionally been the only approach available for composite slabs, known as the MK method. So the limitations of both methods is partial connection approach you can only use it if there's ductile behaviour. The MK method, you can use it for both ductile and brittle behaviour. So at first you might think, well, hey, if you can use it for both, why not stick to the M&K? The only downside of the M&K method is it isn't terribly well suited for conditions which are different to the actual test. So it tends to suffer badly when you have point loads or concentrated loads on the slab. You tend to get some very strange results. So because of that, the partial connection approach is the preferred method. Also, it does tend to have a more of a mechanical basis as well. So if we're talking about slabs, obviously we have to also talk about fire. And when we talk about fire, there's a standard, some of you might be familiar with, AS 1530, part 4. And it's no good actually saying, well, a member has to be tested to this standard, because it doesn't give you all the information that you need. So basically what it tells you is about the criteria for failure, which is normally structural adequacy or load bearing capacity, right? It doesn't fall down. Integrity means you don't get a passage of flame or hot gases, so you don't have cracks opening up. And so if you have filing cabinets, things igniting, or you don't want to have insulation failure. So again, it's the top surface of the slab gets so hot that you could get ignition of carpets, etc. And that's shown schematically here with a rather badly drawn fired egg on the top right-hand side. So AS 1530 basically gives you the arrangement of the devices to measure the temperature, which are known as thermocouples. It tells you about the temperature time curve that you should subject the specimen to, but it doesn't really tell you much about what the fire test specimen should look like. And that's the reason in 2327 that we've formalised that by actually having an appendix that gives you a standard test arrangement. And this arrangement's been in use definitely in the UK for the last 30 years. And essentially what it's intended to do is represent the worst case of a slab at the edge of a building. So you would basically have some continuity of the slab at the first internal support. So basically what the test setup on the left-hand side has is that you have the specimen over a furnace. The span of the slab is loaded, and at the far end, the slab is held down in position. So basically, as the slab deflects, it stops the end of the specimen lifting up, so you actually get hogging moments developing over that internal support. And some pictures of a real test that I was involved in the UK, shown at the bottom here. So the bottom left one is the test specimen. This is it after it's installed over the furnace, and these are the loads. And this is at the end of the test, they tend to open the furnace door just to get the furnace to cool down quickly. And I took this picture very quickly without my camera melting, but that's essentially at the end of the test. So it's unfortunately, it's a pretty unspectacular test. Nothing really happens, but it's a way of actually measuring the fire resistance of the floor. So essentially, what's done in most manufacturers' design tables is that it normally assumes that you can get a plastic collapse mechanism forming in fire conditions. And top right basically shows what the slab looks like after a loaded fire test. So it's not such a severe deflection as you might think. The thing to watch though for these ones is that a lot of these tests are sometimes used to give manufacturers a bit of a competitive advantage. Some manufacturers have found that because they've got such good bonds between the concrete and the steel sheeting, they can actually use that the steel sheeting in fire conditions to still reinforce the slab in sagging conditions. So one thing to watch for that is that if there's ever a substitution, you have to be very careful that the deck that or the manufacturer you're substituting to has done similar fire tests. Otherwise, you may well have to include bars within the ribs of the sheeting. The other thing to watch also is, again, to try and get some competitive advantage. Most manufacturers try and do the tests at the thinnest slab possible, and often they go beyond go to smaller slab depths than's recommended in ASINZS 2327, which is shown here in this table. And again, it's to give them a bit more of a competitive advantage against other manufacturers. So one thing to watch is be very careful if there's any substitution on any of your jobs. So there's a lot of hard calculations in 2327. Well, when I say hard, it can be a bit tedious doing hand calculations. So one of the things that HERA's been investing in is to make things easier for you. And we're just about to launch a new web-based design tool, which designs not only the beams, but will design the slabs as well. And this is just some screenshots of what it will look like. So it's almost ready to launch. We're at the beta testing stage at the moment. We expect to be able to make that available next month. And it's definitely on my onus because I can't leave until this is finished. So I've really got to pull my finger out. Okay, moving on to composite columns. So why use composite columns? They tend to have you tend to be able to provide much more slender, attractive lines. Because of the confinement of the steel tube, you end up getting a bit more capacity out your concrete core. The concrete also prevents local buckling of the steel tube, and they also provide excellent fire resistance without the need to provide applied fire protection. And again, similar to what we did for beams and studs, this was again, we ended up doing some reliability work on this again, to go back to scratch. So Eurocode 4 only permits cylinder strengths up to 60 megapascals and yield strengths up to 460 megapascals. To enable us still to apply the rules to 100 and 690 megapascal concrete and steel respectively, we also did some reliability work. As well as coming up with some the correct capacity reduction factors, we're also able to get some bit more generous B over T and D over T ratios when we're talking about local buckling effects. So there's some, as well as just the safety factors, there are some additional enhancements which are in 2327 and 5100 part 6. So the only downside with composite columns, again, is probably the computational effort. And essentially, if you're to, you need to develop a moment uniaxial load interaction curve given by this polygon A, B, C, D. And essentially, the bending moments that would occur at A, B, and C, and D are shown on the right-hand side. And to develop that curve, you basically have to work out the capacity and axial force for each one of those to be able to do the calculations. And essentially you're looking at it from a member point of view. So this NUS shown on the vertical axis is basically the buckling resistance of the member, and essentially because of the because you've got initial bow imperfections when you're looking at buckling, the amount of moment that you've got to resist is given by this dimension MRX. So I know some people have actually got that confused and just think that they can actually take that full distance from the far left-hand side all the way over to the interaction diagram. You shouldn't really do that because you're actually, you've already utilised some of the bending capacity of the cross-section just through initial bow imperfections. When it comes to fire design, there's 3 different options in 2327. There's level 1, which is tabulated data, and an example is shown on the top right-hand side. It's limited, but it gives you safe designs. So this is from, I think, 30 up to 240 minutes fire resistance. The other extreme end is advanced calculation models, and that will be using finite element analysis. This picture on the bottom left is basically showing the isotherms within a quarter of a rectangular hollow section, and it gets hot at the extremity, it gets cooler as you go into the column. And then the sort of the in-between one is the simple calculation method, where basically there's some rules in 2327 that allow you to get an average temperature of that whole cross-section to be able to do the calculations. And again, as I said, because of the computational effort, HERA has also developed some software, free software again, and this is already available from HERA, and this basically designs the columns to 2327 both for ambient temperature and fire conditions. So I mentioned at the beginning that we did a lot of reliability work, and one of the headaches that we had when we were doing the bridge standard 5100 part 6 was that most of the bridge designers here in New Zealand wanted the same stills that have been recognised for the last 20 to 30 years here in New Zealand, namely European stills conforming to European product standards, as well as stills conforming to Japanese standards. And obviously the domestic steel producers on the committee really didn't like the idea of introducing that. They prefer that we kept to Australian New Zealand standards. And one of the claims that they had of actually against the introduction of these stills was that it could cause an erosion of safety. So because we've done all that reliability work already for the calibration of the standard, to investigate whether it could actually cause any erosion of safety, we actually did some reliability analysis looking at the effect of the different tolerances that are permitted in the European standards and the Japanese standards. And drum roll please, we basically didn't find any difference at all. So although it took a bit of effort, it basically demonstrated that the practice that's been used in New Zealand for the last 30 or 40 years is fine, it's safe, and what we did was in the bridge standard, where there's an appendix on that gives you advice what to do when you're considering these stills. The only unfortunate thing for me was that most of the Australian stakeholders, after this work was done, were willing to have a joint appendix that should allow these alternative stills. Unfortunately, at the very last hurdle, they had a change of view, and it's now only a New Zealand only appendix. But anyway, we gave it a good go. However, one of the other interesting things from this work is the, as you probably might be aware, conformity of still has created quite a bit of attention recently. There's an ASINZS HERA publication now which is a free download shown on the top right-hand side, to look at assessing the compliance of steel manufactured to ASINZS standards. And from all that reliability work we did for the design standards, we actually looked at these alternative steels again, but doing a reverse reliability analysis to look at the amount of tests that you would need to undertake to achieve a particular capacity reduction factor. So all the work is given in this, this journal paper. It's a free download, which I'm sure you'll be pleased to hear. And essentially those rules are currently being implemented within a second design guide, which will be published by here in ASINZS. I understand it will be ready before the close of this year. So the other thing that's been added in the bridge standard is we've redone the fatigue provisions. Again, it was a bit bleeding edge literally, in that we've made there's a few teething problems which Becca kindly have spotted, and those are currently being considered. And essentially, what the two changes to the fatigue provisions are: one, there's a lot clearer requirements on how to make some of these fatigue details work in terms of the preparation, the amount of NDT that's required. And the other thing that's been introduced is what's known as the damage equivalent factor design method. So essentially it's quite a simple calculation process which most engineers could do, I won't say literally on the back of a fag packet, and probably is not very politically correct to say that anymore, but it's a very simple method, and I think what it tends to do is it gives people a bit more of a better feel of what they're doing when they're doing fatigue calculations. It doesn't get away from the traditional minus summation. That's still also available, and you can still use that if you want to get every last ounce out of a bridge. But this method here is really intended to be a bit more user-friendly, and that's why we introduced it. Coming towards a little bit at the end now. I've sort of run over by 10-15 minutes. Now just move on to some of the new stuff I've been doing, or we've been doing since before departing. So we're doing some work on brittle fracture again, and this actually came up from some consultancy work that we did for the Scott Antarctic station, where they were concerned that the existing 3404 and 4100 provisions didn't suit their requirements, and we've come up with some new rules which they're similar to the European approach, but they go beyond those. They're applicable up to down to minus 120 degrees Celsius, and one of the important things of doing this work was that the existing brittle fracture provisions, it normally just relies on notch toughness. It doesn't look at other things that would affect the behaviour of the steel, such as welding, detailing, utilisation, seismic loading rates, cold forming and defects. So those are all wrapped up in this methodology, and again, we've tried to make it simple. It's really just there's just a set of tables that are presented, that all you need to do is look up your grade of steel and the subgrade, and then from that you can say, well, what's the temperature you're wanting to operate at, and this gives you the maximum thickness that's permitted at that particular service temperature. So it's a very, very straightforward method of actually of assessing brittle fracture. So as well as going down as far as 120 degrees Celsius, the other innovation is that it's also applicable to quench and tempered steel, so steels going up to 690 megapascals. And then the last one been working on, and this was from did some work with some Swedish researchers based in the University of Luleå, which is near the the Arctic Circle. And essentially, in Europe, there's a bit of a problem now that we've got a lot of bridge assets, and we either have to reassess them and try and keep them going for a bit longer, or pull them down altogether and start again. And one of the methods we've been looking at is to try and make non-composite bridges composite through these post-installed shear connectors. So in the green box that shows the different types of shear connectors that could be used in bridges. So left-hand side's the headed stud, and most of those are quite invasive, that you'd normally have to break out the concrete to install them. And the connector that we've been looking at is this, what's known as this cold spring pin. And it's the nice thing with this is that it's installed from through the soffit of the bridge into the concrete, and it's basically because it's a spring, it's basically press fitted in. There's no sort of wet work required. So just to show you what it would look, so if we had an existing bridge looking like this, the pavement, water insulation, slab and steel girder. Normally you would actually have to break it out, install the shear connectors, probably have to lace some bars across, and it gets a bit messy. The alternative with these cold spring pins is essentially you have a precision drill through the top flange of the steel girder into the concrete, and then the pins are then press fitted into the concrete. Obviously, there'll have to be some sort of corrosion protection applied to the underside, but other than that, that's job done. So again, doing some push tests. So there've been some comparative tests of these pins versus headed stud connectors. You can see the pins are slightly lower capacity than the studs, but not by much, roughly about 80%. And we've also done some fatigue tests as well, and they perform well. And if you're interested, there's a reference there which describes the work. And interestingly, the first author of this has just actually won the International Association for Bridge and Structural Engineering prize. So it's an international prize for this particular work. So it's not just fairly academic, it's actually been used on real bridges worldwide. Docklands Light Railway in London, the Tinsley Viaduct in the UK, again, Light Railway again, Vancouver SkyTrain system, and the Pittsburgh Bridge in Sweden. So all of those have used this technique. So that's it for me. Thank you for your attention so far. So in conclusion, 5100 Part 6, the first joint Australian-New Zealand bridge standard, and it's the only joint standard among the 5100 suite of standards. It really has been a catalyst for more harmonisation activities, and really that kicked the ball off on the work on 2327. The other thing is that if some of the rules look a bit strange, it's because we've actually had to go completely from scratch and do reliability analysis for all of those. So when I say strange, they might look a bit different to other international standards, but the reason is because we're using much higher strengths. And hopefully I've just given you a bit of a taste of some of the future improvements that will be included in these standards. And very, very last of all, one little plug. Amir mentioned it at the beginning. As well as being chair of the national group of IABSI here in New Zealand, I also won a New Zealand bid to host it here in Christchurch. So if you're interested, it's going to be next year, 2nd to 4th of September 2020. And if you're interested in submitting an abstract for it, these will be these are the dates. The actual the website is open now, so if you're interested, you can start registering as of today. Thanks for your attention. Cheers.